friends, welcome to the YouTube channel All About Electronics. So in this video, we will talk about the bias stabilization and the stability factor of the BJT. And we will find out the stability factor for the fixed bias configuration. So the stability of any circuit is the measure of how sensitive the circuit is to the variation in the external parameters. And for BJT, this stability is very important parameter, particularly whenever it is used as an amplifier. So for BJT, the collector current IC is sensitive to the following parameters, and as the temperature changes, the value of these parameters also change, and the change in any of these parameters can cause the drift in the design operating point. For example, as the temperature increases, the value of beta will also increase. Similarly, with the increase in the temperature, the voltage between the base emitter junction will reduce. And this reverse saturation current also increases with the rise in the temperature. And in fact, this reverse saturation current almost gets double in a value with every 10-degree rise in the temperature. So due to the change in all these parameters, the collector current IC also changes. So let us take one simple example, and through the example let us understand how the change in the value of beta and the reverse saturation current changes this collector current. So for that, we will assume that the BJT is biased in the fixed bias configuration. So let's say for the fixed bias configuration, the base current IB is set to 30 microampere, and at 25 degrees centigrade, for the given value of beta, the operating point is almost set at the center of the load line. And here, this is the reverse saturation current at T is equal to 25 degrees centigrade. Now if the temperature increases to 100 degrees centigrade, then both beta and the reverse saturation current will increase. So now if you see at 100 degrees centigrade, then the value of this reverse saturation current is more. And also due to the increase in the value of beta, the spacing between the curves will also increase because IC is equal to beta times IP. So due to that, now the collector curves will look like this. Now here, as the BJT is biased in the fixed bias configuration, so the value of base current IB is directly proportional to the base resistance. And over here, of course, we are assuming that the voltage VBE is not changing with the temperature. That means the value of base current IB will still remain 30 microampere. So due to that, with the increase in the value of beta, now the collector current IC has been increased. And now the operating point has moved towards the saturation. And now suppose if we use the same circuit for the amplification at this temperature, then there will be a considerable distortion in the output. And that is why to operate the BJT in environment where the temperature is changing continuously, the stability is very important parameter. So the stability of the BJT circuit is defined by the stability factor. And as there are three factors that affects the operating point, so there are three stability factors. The first stability factor defines how the collector current changes with the change in the reverse saturation current. And during the calculation of this factor, it has been assumed that the other two parameters, that means the voltage VBE and the beta, are constant. Similarly, the second stability factor defines the change in the collector current with the change in the voltage VBE. While the third stability factor defines the change in the collector current with the change in the beta. And many times these stability factors are defined by the symbol S, S dash and the S double dash. So if the stability factor of the circuit is high, then the circuit is more sensitive to the change in the external parameters. That means for the stable circuit, the low stability factor is desirable. So now let us find out the stability factor for the fixed bias configuration. Now in the earlier video, we have already derived the expressions for the base current, the collector current and the voltage VC for this fixed bias configuration. Now during the DC analysis of the circuit, usually when we write this collector current, then we write it as IC is equal to beta times IB. But actually it is given by this expression. But for the silicon transistors, as this reverse saturation current is in the nanoampere range, so the second term is often neglected. But here, as we are interested in finding the change in the collector current due to the change in this reverse saturation current, So let us also write down the second term. So now let us put the value of this base current into this expression. That means the collector current IC can be given as beta times voltage VBB minus VBE divided by RB plus beta plus 1 times ICBO. So this is the expression of the collector current in terms of the beta, the VBE and the ICBO. So first of all, now let us find out the stability factor S for the fixed bias configuration. So the stability factor S can be given as del IC divided by del ICBO. And here we are assuming that voltage VBE and the beta are fixed. Now in this expression, the voltage VBB and RB are already fixed. And here we are also assuming that voltage VBE and the beta are fixed. That means whenever we differentiate this expression with respect to ICBO, then the first term will become 0. That means del IC divided by del ICBO is equal to 0 plus beta plus 1. That means for the fixed bias configuration, the stability factor S is equal to beta plus 1. Similarly, now let us find out the stability factor S dash for the fixed bias configuration. So this stability factor S dash can be given as del IC divided by del VBE. And during the calculation, we are assuming that the beta and the reverse saturation current ICBO are fixed. Now here this collector current IC can also be written as beta times VBB divided by RB minus beta times VBE divided by RB plus beta plus 1 times ICBO. Now in this expression, the first term and the last term are constant. So whenever we differentiate IC with respect to VBE, then the first term and the last term will become 0. That means del IC divided by del VBE is equal to minus beta divided by RB. That means for the fixed bias configuration, the stability factor S dash is equal to minus beta divided by RB. And similarly, now let us also find out the stability factor S double dash. So the stability factor S double dash can be given as del IC divided by del beta while keeping the value of voltage VBE and the ICBO fixed. Now this collector current IC can also be written as beta times IB plus beta times ICBO plus ICBO. And whenever we differentiate this term with respect to beta, then del IC divided by del beta is equal to IB plus ICBO. Now as I said earlier, typically the ICBO is in the range of nanoampere. So approximately we can say that this del IC divided by del beta is equal to IB, or we can say that it is equal to IC divided by beta. So in this way, we got the expressions for the three stability factors S, S dash and the S double dash. So now the total change in the collector current, that is the delta IC, can be given as S times delta ICBO plus S dash times delta VBE plus S double dash times delta beta. And now let us see if there is any change in the temperature, then how these factors can affect the collector current. So let's say we have the value of beta, the VBE and the ICBO at the two different temperatures. And with the given values of RB and the RC, the collector current IC in the fixed bias configuration is equal to 1.74 milliampere. And now if the same circuit is operating at the 100 degree centigrade, then let us find out the change in the collector current due to the change in all these parameters. So as I said, this delta IC can be written as S times delta ICBO plus S dash times delta VBE plus S double dash times delta beta. And if you put the values of this S, S dash and S double dash, then we can write this delta IC as beta plus 1 times delta ICBO plus minus of beta divided by RB times delta VBE plus IC divided by beta times delta beta. Now here, if you see, whenever the circuit is operating at the 100 degree centigrade, then the reverse saturation current will become 20 nanoampere. That means the change in the current is equal to 19.9 nanoampere. And here at the 25 degree centigrade, the value of beta is equal to 50, while the base current IB is equal to 250 kilo ohm. Similarly, the change in the VBE is equal to minus 0.2 volt. So if you put the values of all these parameters, then the change in the collector current IC is equal to 51 times 19.9 nanoampere plus minus 50 divided by 250 kilo ohm times minus 0.2 volt plus 1.74 milliampere times 30 divided by 50. That means delta IC is equal to 1.015 microampere plus 40 microampere plus 1044 microampere. So this is the change in the collector current due to the different parameters. And as you can see over here, the major contributing factor is the change in the value of beta. That means the maximum change in the collector current IC will occur due to the change in the value of beta. And in fact, that is why during the DC analysis of this circuit, we had given the more emphasis on the change in the value of beta. So the designed biasing circuit should be such that even if there is a change in the temperature, there should be a minimum change in the operating point. So in the next couple of videos, we will find out the stability factors for the voltage divider biasing configuration and similarly for the collector feedback biasing configuration. But I hope in this video, you got the general overview of the bias stabilization and how we can find the stability factors for the fixed bias configuration. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.